going to do our first study of a quantum field theory. And the quantum field theory we're going to look at is the simplest one you could imagine. It's this free field theory whose classical equations of motion gave rise to the Klein-Gordon equation. So this is free field theory. We computed that we've got a classical Hamiltonian, which we want to turn into a quantum Hamiltonian that looks like the following. And we've got the operators So remember, the fields get turned into quantum operators. The operators are functions just of space and not of time, because we've explicitly broken Lorentz invariance in going to the Hamiltonian picture. And we're working in the Schrödinger representation. And quantum field theory is no different from quantum mechanics. If we're in the Schrödinger representation, these guys don't depend on time. Okay? So again, X is just a label telling us which of the infinite number of operators we're considering. So these are the commutation relations. Okay? And at the very end of the last lecture, I ran through the harmonic oscillator, solving it using creation and annihilation operators. What we're going to do is exactly the same thing here. We'll use exactly the same tricks, and we'll see that we can solve it in exactly the same way. And then we'll interpret what that solution means. Okay? So for the harmonic oscillator, you write A and A dagger. You define A and A dagger in terms of P's and Q's. But of course, it's easy to invert that and get P's and Q's in terms of A's and A daggers. So let me write down the analogous expression to this for the free field theory. So we'll define an infinite set of creation and annihilation operators. They're going to be labeled by a 3-vector, which I'll call P. And the definition, I could give the definition either way, but it's going to be easier to do it this way. So the definition is that I'm going to write phi of x as okay, so you can take this to be a definition of the A's and the A daggers. Let me just stress the operators here are these guys, the A's and the A daggers. This thing here is just a function, or if you like, telling you a labeling between the operators. This X labels which operator we have here, and this P labels which operator we have for the A's. And this is the relationship between them. Finally, let me just remind you what this thing omega p is. If you look back to the last lecture, it was actually I did something a bit different. I defined it as the positive square root of this. Okay, so you can just take this as definitions of A's and A daggers. It's motivated by two things. It's motivated firstly by us realizing at the end of the last lecture that if you did a Fourier transform on phi, the Klein-Gordon equation just became a bunch of harmonic oscillator equations and was solved by just some sines and causes. Okay? So that's where this Fourier transform comes from. And then secondly, it's motivated by solving the quantum harmonic oscillator.
So that's the inverse Fourier transform?
So if you wanted to get A's and A daggers in terms of phi's and pi's, you'll just have to do an inverse Fourier transform. Okay? And there's no subtleties going on here because what these are operators, but everything we're integrating over is just a function. Okay, so it's just sort of a sum of operators. An integration over P is just a sum of different operators. Okay? Okay. Yeah, please.
A and A dagger are, well, the A dagger is A dagger.
Oh, good. Yeah, that's a good question. I should have stressed this. Phi is Hermitian and pi is Hermitian. These were real scalar fields, so they should be Hermitian. And this works as long as A dagger is the Hermitian of A. Did I get that right, or is there a minus sign on the P's there? No, that's right. There's a minus sign here, which ensures that A dagger is A dagger. Okay? Because this becomes plus, and this then becomes this, and then phi is phi dagger. You see that? Yeah. So phi and pi are Hermitian conjugates as long as A dagger is the Hermitian conjugate of A. Okay. Other questions? Good. So let's just take these definitions and plug them into the various identities, which I unfortunately just rubbed off, and see what we get. So the commutation relations are basically that phi of x, phi of y is pi of x, pi of y is 0, and then the interesting one is that phi and pi don't quite commute when x is equal to y. Okay. So what do we do for the harmonic oscillator? We have these commutation relations for Q and P. We plug in these expressions, and we basically get that A commutator A dagger is equal to 1. So we're going to do exactly the same thing here. We're going to plug these definitions into this to find commutation relations for A and A dagger. What we find is that all the A's commute with all the other A's, and all the A daggers commute with all the other A daggers, but the A's and the A daggers don't quite commute with each other. And it's exactly as you would expect. The only small subtlety is that there's a 2 pi cubed that comes here, and that comes from my definition of the Fourier transform. Okay. And I'm going to leave the proof of this as an exercise. It shouldn't take too long. It's really just a question of remembering what Fourier transforms are, and in particular, what the Fourier transform of the delta function is. So the fact that the integral of the 3p e to the I p dot x gives you the delta function of x. Okay, that'll give you these. I'm going to set lots of trivial exercises like this in this lecture, and they're all basically exactly the same flavor, plugging things in and doing integrals over x or p to do inverse Fourier transforms, basically. Okay, any questions about this? So it's a bit mechanical. Let's have a look at the Hamiltonian. Actually, I will go through on the board this sort of same basic exercise for the Hamiltonian. So the Hamiltonian is a half times the integral of d3x pi squared plus grad phi squared plus m squared phi squared. And all I'm going to do is just plug into this the definitions for phi and pi in terms of a and a dash. So what do we get? It's quadratic, and each of the fields is going to come with its own Fourier transforms. So each of the pi's is going to one of them is going to come with an integral of d3p, and the other one I'll call the integral of d3q. Okay. So, well, you know, the expressions for phi and pi are roughly the same as the expressions for q and p. So certainly where the factors of the square root of omega are exactly the same. So pi squared is going to come with 2 square roots of omegas on the top. And so if you just, there's a minus sign because there was an I in the definition. Okay, that's the pi squared term. The grad phi term, well, there's a 1 over square roots of omegas rather than them being on the top. That's this statement here. It comes with a grad, so the grad pulls down a factor of the momentum from inside the Fourier expansion. Okay, and then there's one last term. Oh, by the way, let me just stress here that there's lots of vector indices. This vector is dotted with this vector, of course. This guy has a vector index, but it's not dotted with anything. It's just labeling which A we are, and it's being integrated over here. But this guy has a floating vector index, which is dotted with this Q here. That's because this grad is dotted with the other grad. Okay. So the final term is the m squared term. Q, A, P. Okay, so it's kind of tedious. You can see what I've done, right? Just plugged it in. Now comes the kind of step that you have to do for all these calculations. So what do? It's the usual Fourier transform kind of issues. you do the integration over d3x first. Okay? So where's x appearing? It's appearing just here and here. So what's the integration over d3x going to give us? Well, it's just everything else you could ignore, and it's just the integration of e to the I something times x, so it gives us a delta function on that something. So doing the integration over d3x on this term is going to give us a delta function of p plus q. And doing the integration over d3x on this cross term here is going to give the delta function p minus q. Okay? And similarly here it's going to be minus p plus q, and here minus p minus q. Okay? So that happens for each of these. Okay, when you've got the question, I'll come back. Good. So, what do? We collect all of these things together, and there's two different terms. Okay, so what have I done here? I've done the integration over d3x to give me the delta function of a p and a q, and then you use that delta function to do the integration over q. Okay, so you kill two of these in one go. So there's two different terms here. One of them are the terms that you get when p is equal to q because of the delta function, and the other one is when p is equal to minus q because of the delta function. Okay, so this was the guy that came from a delta function of delta p plus q, which tells us that q is equal to minus p. And this was the guy that came from delta functions p minus q, which tells us that q is equal to p. Okay, is that clear? Is the question?
What delta function gave us the q equals negative p?
Q equals negative p came from, say, these two terms. This was giving us a delta function of p plus q. Yeah.
Because the commutator.
Delta 3 p plus q is what you're getting from this. And the same thing from this, but with minus sign, because it's inside the delta function. Yeah. So these terms and these terms, and these terms and these terms gave us everything on this line, and then it was the cross terms which gave us this. Okay, is this clear? Boring, but so now comes the final step. It's just to notice that the definition of this guy was equal to p squared plus m squared. So this term vanishes. So this is the Hamiltonian that we get. Okay, so this again is the statement that the free field is just an infinite number of harmonic oscillators. See, if I cross out the integration here, all I've got is, for a given fixed p, the Hamiltonian for a harmonic oscillator. In particular, there's no interaction terms between creation and annihilation operators that have different p's. You know, one p only interacts with a dagger of the same p in the Hamiltonian. Okay. And then I do this integration here, and the integration is nothing to be worried about. It's just a sum, but you know, there's a continuum of these harmonic oscillators, so it's a continuous sum or an integration. Okay, is this clear? Are there questions? Now there's one other thing we can do, which is try and get the Hamiltonian in the same way as this, to get this sort of ground state energy here. And remember, the way we do this is we take this and we commute them past each other and then just double up with this. So we could also write this as 2 pi cubed omega p a dagger p a dagger, sorry, a dagger p a plus except now there's a slight problem, because remember, commuting a and a dagger past each other, well, they commute unless you know, the index on this is the same as the index on that. And if that's true, then you get a delta function. It's a delta function evaluated at 0, and that's infinity. So we've sort of got this infinity arising here. But it's clear where it's coming from. It's coming because we have a continuum of these harmonic oscillators. So there's an infinite number of them, and that's why there's an infinity. So what I want to do now is just kind of spend some time looking at what this infinity actually means. Sorry, say again?
That on again, or is that times the delta there?
This should have been sitting there. Yes.
Since the delta is under inside the integral, it's not really an infinity we need to worry about, because the integral of anything is with a delta. The area under it is 1, so when we integrate any function into a delta function,
it's not. We don't have a delta of p. It's actually an infinity, and then we're integrating this infinity an infinite amount of times. So it's actually two infinities.
yeah.
We're going to tease this infinity apart right now. It's a lot of infinity. Okay, questions? Yeah.
So we define our Hamiltonian just following our intuition. And then we end up at this point where we found our Hamiltonian is infinity, and now we're going to try and normalize it and cut off the rest.
Exactly.
But why don't we go back and say, well, maybe our Hamiltonian was wrong, and let's write a new Hamiltonian that's better?
We could do that.
Conceptually, that would normally be the logical path, right?
We'll discuss these issues. Okay, you could absolutely do that. But I'll mention it. Yeah.
Sorry, I missed the logic between the step on the top of the board and the step right under it.
This is AP, A dagger Q. Let me just make sure I get my minus signs right. Two pi cubed, delta 3, t minus q.
Oh,
so it's this,
yeah,
p is equal
okay.
to q, which is giving us this delta.
Yeah, thanks.
We're going to come to exactly what the interpretation of this term is now.
Well, I'm just wondering. Okay, so in the first expression, we have two terms. And if you split up the integrals, they're two unproblematic terms, except they're the right versions. So
this is the same as this, and now I'm going to tell you how to interpret this.
well, I'm just okay. Maybe. Like, I don't see why you have to worry about that delta. If you can just make it go away by not.
Well, when you wait 5 minutes, and then we'll come to talk about this delta function, then you can re-answer the questions. Is that good? Other questions? Okay, so how do we understand this? So let's look at the simplest state in this theory, which is going to be the vacuum state. And we're going to define this vacuum state in exactly the same way as we do in the harmonic oscillator. And it's that it's just going to be killed by all the annihilation operators. And in particular, I really mean all the annihilation operators. So there's an infinite number of these guys labeled by a 3-vector p. Every one of them is going to kill this state 0. So let's figure out the energy of this state. Well, we take the Hamiltonian, we act on the vacuum with it. This term kills it, but this term is a big number. Yeah, good. So this is the state of the field, right? So it's the ground state of the field.
So it's one of those horrible state vectors that we don't ever
Think about explicitly because it's
Yeah. Now in this case, it's simple enough that you could actually write down the wave functionality explicitly. But what we're going to do is not write down wave functions in the Schrödinger language, where the ground state of the harmonic oscillator is e to the minus x squared.
Yeah.
We're going to just write things in this kind of simplified language. But yeah, you're right. It would look a bit messier if you tried to write it down as a wave function. Yeah.
I just wanted to comment, you don't write this explicitly for the same reason that you don't write determinants by using the formula for determinant. You could write it explicitly, but these are defined by their properties. So this is writing it like in an explicit way by telling you what it is.
Okay.
poor choice of words.
Other questions? Yeah.
No.
So this is obviously infinite. So what to say? The first thing is, oh, sorry.
Why would such a state exist? Like, if you see that the energy is infinite, you can wonder whether it had the right to consider it.
Good. So the energy is going to be infinite for any state at all, because the Hamiltonian. Yeah. If the infinity is your worry, then hold off because we're going to explain it now, and just explain why it's not.
No, but my worry is kind of the same as Alex's worry. It's like we have infinities and we're trying to get rid of them afterwards. But like, why would we try to get rid of them if we can just avoid constantly?
You'll find that with this Hamiltonian, every single state has. This is going to be the state of lowest energy possible, and every state has.
Lowest positive energy.
No, so you have the other option, which is to try and construct some sort of Hilbert space that isn't bounded below.
Yeah.
And then you're maybe thinking that if you go all the way down to minus infinity, you can cancel that infinity with this infinity. Nothing that complicated is needed. We're just going to see that we're going to throw this away, and I'll explain now what it means and why we can throw it away and why it's really okay. So there's no need to get hung up on this infinity. It's just going to disappear very quickly. Okay, so the first thing to say is that there are lots and lots of infinities in quantum fields. And they're all our faults, right? Because we put them in at the beginning. We're dealing with an infinite number of degrees of freedom. That's where they're coming from. They're also what gives rise to all the richness and beauty in quantum fields. However, this one doesn't really fall into this category. This one's completely trivial, and what we're going to do now is just sort of show what it's telling us and why we should ignore it. Okay, so there's actually two infinities hidden here, which I've already mentioned. There's one coming from the fact that this is a delta function evaluated at 0, which is infinity. And there's another coming from the fact we're integrating here, which gives us another infinity. And they mean something a little bit different. So let's just understand now what these two infinities are telling us. So the first infinity is just there because space is big. Okay, so what do I mean by that? I mean big in that way. Okay, it's infinite in extent. No, I actually mean physical space is big. Yeah. It's this guy that's due to the fact that physical space is big. So let's understand why this is. By the way, let me just tell you a name because you'll see it later. So these are typically called infrared divergences. Here, this is so trivial that it almost doesn't deserve this name, infrared divergences. But you will come across these kind of things in other contexts. Yeah.
Integrate over the whole thing.
So why don't we deal with?
Why don't we just try to do like densities?
You're about 3 minutes ahead of.
Okay.
Yeah. So let's have a look. Let's consider a box of size L. And let's look at the definition of this delta function, such a box. Well, eventually we're going to take our box to infinity. So this infinite delta function, well, is defined in the following way, where you take the size of the box to infinity. But if this is 0 here, because, sorry, if this is 1 because p is 0, then it's very clear what this is. This is just the size of the box. Yeah.
I'm sorry, this is a little bit of but how does the delta function know about the box? Like, how did it always?
No, I'm telling you that there's an interpretation of this delta function. 2 pi cubed times delta 0 is really just the volume of infinite space. So what it knows about is the fact that the space we were considering is infinite, because the Hamiltonian was integrated over all of space. So that's where this delta function is coming from the fact that we were considering an energy over all of space, and not, as was pointed out,
So-
an object.
So you're saying that if we started, if we went back and did our calculation in a box instead of,
You would have found,
we never would have come up with.
you wouldn't have got this delta function, you would have just got a V, where V is the volume of the box.
Yeah.
Okay, so that's not saying something that's true in general about delta functions. It's saying something about the process we use to get that.
Get this particular delta.
Okay. Hey. Sorry.
So the ground state energy okay. So as you pointed out, of course it's infinite because it was an energy integrated over all of space and not an energy density. And so of course what we should really be thinking about, and let me make sure my 2 pi's are correct. 2 pi cubed is energy densities. Okay. So at least one of these infinities, this delta zero, we just saw was completely trivial because we were working with total energy and not energy densities. Is that clear? People happy with this? But the expression we have for the energy density is still infinite. And this time it's an ultraviolet divergence, meaning that it's not coming from the fact space is big in that direction. It's coming from the fact that space is infinite in this direction. In other words, we can have as infinitesimally small separations in space, or correspondingly after the Fourier transform, as higher energy as we want, a higher momentum mode. So fields which fluctuate on very, very small distance scales have very large p, and that's where this integral is diverging. Remember that this guy here is just defined to be this. So divergences in quantum field theory that come from very large momenta, or very small fluctuations of the field, fluctuations on small distance scales, these are called ultraviolet divergences. Okay, so where's this guy coming from? Well, again, it's sort of our fault. We put it in. All theories of physics have divergences, right? If you look at classical electrodynamics, when the electron gets infinitely close to the proton, it's getting an infinite energy. Of course, because some angular momentum barrier. You know what I'm saying? If you just
just like because the energy gets infinite.
Right. The point is that in classical mechanics, we can avoid those singularities. Quantum mechanics, though, the wave function is exploring everywhere, and so basically this is where this divergence is. Okay. Now, in some sense, it's our hubris. We've taken a theory, which is the free-Klein-Gordon theory, or any other quantum field theory, and we're sort of assuming this field theory makes sense up to arbitrarily large energy scales, arbitrarily small distance scales. And that's got to be wrong. There's no reason at all why we should have a theory which works on all energy scales, all distance scales. So what we need to do is to find a way to deal with these kind of divergences. And this is the whole story of renormalization. There's sort of two sides to the story. One is the fact that there's a way to sort of get rid of these infinities and calculate and get sensible answers. That's what Feynman and Schwinger and company did in the 50s. So that's called renormalization. Then there's the perspective from the 1970s, which usually goes by the name of renormalization group. And this is due to Wilson primarily, but building on work of Kadanoff in the 60s. And this is what's telling us that what these infinities are meaning is telling us physics. Okay? So I'm not going to tell you anything about this, but that will be the subject of the second quantum field theory class. I think quantum IB. So for now, we've just got to deal with this infinity. And the way to deal with it is just so this arises because we've assumed our theory is valid on arbitrarily short distances. Okay, so we could, for example, just decide we were going to integrate only up to momenta of a certain amount. Perhaps because, if we're in condensed matter, that's certainly what you do because there's some lattice structure there, and you only integrate up to momenta of order the inverse lattice spacing. However, there's an easy way to deal with this, which, like I said, is we just ignore it. The words we can say for ignoring it is that we're really only interested in energy differences in physics. And this particular infinity is going to be there for every single state we compute. So we may as well just strip it off to begin with, which is, I think, the attitude that you were taking 20 minutes ago. We should just redefine our Hamiltonian so it's not there. So that's exactly what we're going to do. So So we're just going to remove this infinity and redefine the Hamiltonian to be that first term okay, in particular, since the term we've thrown away was constant, it's exactly the same on all states. So now our vacuum just has zero energy by definition. Okay, if anybody feels this is a cheat, then let me just mention that you could land on this Hamiltonian immediately because of ordering issues between going from classical theory to the quantum theory. So for example, let me go over here. If I'd have written this Hamiltonian here as omega q minus IP in the following way, then classically it's clear that this Hamiltonian is the same as this Hamiltonian, right? I just multiply it out, everything commutes with everything, so it's fine. But quantum mechanically, they differ, and they differ precisely because P and Q don't commute. So there's an ambiguity in going from a classical Hamiltonian to a quantum Hamiltonian, and if we just picked this one to begin with, this infinity would never have arisen, and we'd end up on this straight away. Okay? So,
I guess two questions. First of all, did we ever write down a Lagrangian for this system?
Yeah.
Okay, so what's the real Lagrangian? Like, since the one we wrote down clearly doesn't work.
It works fine. And we wrote down on
No,
the very first lecture. We then computed the Hamiltonian, and we then worked through this.
We computed the Hamiltonian, and then we decided to use a different Hamiltonian. So what's
No,
the
we just
different
threw away
Lagrangian?
an overall constant. We computed the classical Lagrangian.
Oh,
Lagrangian's
no,
always
no.
classical.
But we never wrote down a quantum Lagrangian?
I don't know what that means.
Oh, really? Wait, then why are we...
We
why
went
did
from
we
the
talk about-
Lagrangian to the Hamiltonian, the classical Hamiltonian, to the quantum Hamiltonian. And
So-
that's the route we'll always take.
So if there's no such thing as a quantum Lagrangian, why do we talk about Lagrangians in this course?
Because all the symmetries are manifest in the Lagrangian formulation and not in the Hamiltonian.
Okay,
The
but, the classical Lagrangian can't actually... You can't actually use it to find the quantum field theory.
You
because
can use
there's
it, but
regulars.
using the path integral, what sits in the path
Okay.
integral, and you'll
Okay.
deal with that sequence. Question?
I just wanted to say, if we say this, then can I not just say that the ground state cannot be attained? The ground state cannot be attained. The ground state of anything does not exist.
The problem is if you say that, what do you have in
everything that I have, it's just a small excitation on the ground state because we have major energy difference.
Oh, that's true, but why would you want to throw away the ground state but keep everything else? And everything else also suffers from that same infinity.
Because that particular ground state gave us some problems, so we should not go there. Just like no.
Oh, but every single state you would write down would have that same infinity sitting there. So the thing to do is just forget about the infinity. The energy of everything is something physical plus a number which I'll call capital N. Now, you'd be happy to throw away capital N if it was anything other than infinity. So it's infinity in this case. Yeah.
That shouldn't work.
Why not? Which bit?
I mean, throwing away capital N is assuming that N is finite.
No, I'm saying you can do it when N is infinity. It's just you're going to feel a bit queasy.
Well, are you fine dividing by infinity for your B?
Yeah.
How does this Hamiltonian not have the same? How does this Hamiltonian not have the same infinity? Because we're still integrating over all P.
So let's look at the ground state. The ground state is defined by the fact it's killed by the annihilation operators. So this guy kills it and gives 0.
Okay, and then you're integrating 0 over all infinity.
Yeah.
But
Okay, so you're worried about 0 times infinity can be anything you like. So again, regulate this, and then send this to infinity.
Couldn't you just, if you care about all you care about is differences, you could take the difference before you send the limit to infinity, so you have a finite limit, and then you take that limit, and then you don't, then your infinity cancels out before.
You would end up exactly on this.
So it's fine.
So I should say that when you get to more subtle divergences, it's exactly these kind of arguments that you have to do. You have to, it's called regulate the integral, which basically means you're kind of cut off here, although you'll learn that there's, don't integrate to infinity, but integrate to some finite limit. But you'll learn that there's sort of more creative ways to do this regulation. Then you do the calculation, then you send that cut off to infinity, and you see what's there. And sometimes you get very, very surprising results. Yeah.
So I'm sort of thinking on the fly here, so this could be wrong, but it appears that this can be rewritten in terms of the commutator. Like you rewrite it in terms of the commutator and AP better. Yes?
Yeah, you could try playing around with this and rewriting it in terms of other ways, but you might get infinities that get reintroduced.
That's the problem.
Yeah, however, the question is, I've got this nice state here, which was defined in a simple way.
Yeah.
This has the property that it annihilates this. And it has a finite energy. All excitations are also going to have a finite energy.
But
Why don't you just play around with it and see what you can get, and then
I
ask
did,
me.
and what you get is infinity. You rewrite this.
Let's discuss afterwards, okay? Other questions? Okay. Okay, so in general, let me just give a definition. So in free field theory, we define a normal ordered string of operators So suppose I have any bunch of fields evaluated at any point. Then these are now all operators, so the ordering matters. And I'm going to define the normal ordered guys, and whenever I mean normal ordered, I'm going to put colons outside the string of operators. And what this means is, let me just make sure my grammar's right. In free field theory, we define a normal ordered string of operators. We write it like this to be the usual product with all annihilation operators move to the right. Okay, so in particular, so this is just a definition. I'm not going to argue why this is useful at the moment. It's just a definition, but in particular, the Hamiltonian we've chosen could be written unambiguously in this way. Okay, so take any Hamiltonian that you want in here, and then that Hamiltonian that's A dagger plus A dagger A. Putting the colons around it means that you just move all the A's through A daggers with impunity. You don't pick up those delta functions. Okay, so this is what we mean by normal ordering. Just a definition. Okay. Okay, any questions? Yeah, Tiber.
When I redo the problem that we did today, so expand the Hamiltonian, and then all those quadratic expressions of the operators are normal order then, like push the annihilation operator to the right.
Yeah, you just.
I don't use the commutation relationship.
Exactly. This, in some sense, means that A and A daggers commute within colons, because the colon wins and says all A's go to the right.
So after I've done that, then of course I can take the colons off, and if I want to do further manipulation, I'll have to use the commutation relationship.
In fact, we're going to see either tomorrow or Monday how this definition of ordering fits in with various other things through this. Yeah, but
it seems kind of weird, because if you use the commutation relations first, then it is normal order.
Yeah, so I'm just. What? So suppose I give you some funky expression of A's and A daggers, and I tell you to put colons outside. That defines a new expression where all the A's are to the right. Okay. It's just a definition. We're going to see where it's useful. Sure. Okay, so what do we have? I told you we can ignore this infinity. It's clear what this infinity was, by the way. It was just the ground state energies for an infinite number of harmonic oscillators. Right? It was the integral of a half omega integrated over all omega, all frequencies. So you might think that, for fields, the ground state energies just aren't important. We can ignore them. Well, that's not quite true. There's two situations where we think this should be important. Well, one where we know it's important, and one where we think it should be important. The one where we think it should be important is the cosmological constant. Because I lied to you. I said in physics we only care about energy differences, we don't care about energies. That's rubbish as soon as we've got gravity. Gravity couples directly to energy. And so why doesn't gravity see this infinite sum of ground state fluctuations of the quantum fields that we know exist? Now, you could say, well, we only know the quantum field theory is valid up to the TeV scale that we're exploring at the NHC. But surely that means we should have ground state energies up to the TeV scale, and the cosmological constant should be TeV scale. But it's not. It's the minus 3 electrons. So this is the cosmological constant problem in quantum field theory, at least at first pass. It's why these ground state energies, these fluctuations of the quantum fields, aren't gravitating. Why gravity is not seen. The best answer we have so far is that there's some other contribution which cancels. So they are gravitating, but they're cancelled by something else, just a bare cosmological term in the Einstein action. Of course, there's lots of crazy ideas about other ways around it, but I don't think any of them actually are compelling in any way. So this is a big issue. In fact, we've thrown this infinity away. We'll have gravity. That doesn't seem bad. By the way, it seems very unlikely this is a quantum gravity effect. You might think, it's quantum mechanics and gravity, therefore quantum gravity, we don't know. That's rubbish. This is happening at a distant scale, well, the actual cosmological constant is a distance scale of about a micron, maybe 100 microns, something like this. So it doesn't seem that we need quantum gravity. It's not a Planck scale effect. Or maybe there's some subtle reason we need quantum gravity that we're not understanding. Okay, so there's a big problem there. Throwing away zero-point energies in the presence of gravity. The other place where we know that these zero-point energies are important is when you can turn the zero-point energies into an energy difference and not just an overall energy. And that's what happens in the Casimir effect. So in this afternoon's tutorial, you're going to go through the Casimir effect, using this calculation of zero-point energies and computing the force between two parallel plates due to these zero-point energies. Okay? It's a really nice calculation. Okay, so are there any questions about this? If you have questions about how to solve the cosmological constant problem, I probably can't answer. You're good? Okay, so what's next? We've looked at the ground state energy, so now we're going to look at the excited states, and we're going to see why we can interpret these excited states as particles. Okay. So remember the harmonic oscillator. How do you understand excited states? You do the commutation of H and A, and you see that it's equal to A, and that means that you can sort of take any energy eigenstate and raise it or lower it with A's and A daggers and get a new energy eigenstate. So the same is true here. We've got an infinite number of raising and lowering operators, and they're commutators with H. Given by the following. Exactly the same as for the harmonic oscillator. It means that all I've got to do is take the ground state and act with the creation operators to get an excited state that's an eigenstate of the Hamiltonian. So I'm going to have a name for these excited states. If I act on the ground state with a dagger labeled by the 3-vector P, I'm just going to call that the state P. What's the Hamiltonian for this? Or what's the energy of this state? The Hamiltonian acting on P is just omega P. We had a definition of omega P. It was equal to this. Okay, but this should be very familiar. This is the energy dispersion for a massive particle in Minkowski space, relativistic particle with mass m and momentum p. Okay? This is the relativistic dispersion relation. And 3 momentum p.
The dispersion relation? I mean, it's arbitrary, right?
It's arbitrary. No, what I'm saying is that this is an equation you've seen before. Let me rewrite it here. So this is the equation for the energy of a particle with 3 momentum p and mass m. Here, this is the energy, meaning it's the eigenstate of the Hamiltonian, and it's equal to this. So what I'm noticing is just the coincidence between this equation and this equation. Is that good? Yeah. Okay, so this is going to motivate us to interpret this state as the state of a single particle with 3 momentum p and mass m. So it certainly has the right energy to have that interpretation, and now we're going to see that it has the other characteristics that one would expect from a particle of momentum p and mass m. Okay. Somebody asked me the question yesterday. It might have been you. The question was, there's an m squared phi squared in the potential for the field, and is that m the mass? And I said, no, that m isn't the mass. Okay. Now I've changed my mind. So it wasn't the mass until now. It's just the term m squared phi squared in the potential. When you quantize, what it gives you is that the mass of the quantum particle is m.
So that's only for the phi part?
It's going to turn out that for any field you want to write down at all, the quadratic term that doesn't have any derivatives, the coefficient of that up to a factor of a half is always going to be the mass. Actually, sometimes it's an m instead of an m squared, but we'll find out why that is. But the coefficient is always related to the mass, and sometimes it's the mass squared, and sometimes it's just the mass. No, it was an m squared in the Klein-Gordon equation. In the Dirac equation, it's an m. So we'll get to that next week. Okay, so what else could we check? I've created this state, and I'm telling you that the correct interpretation of this state, which is the first excited state of this quantum field, is that it's a particle of mass m traveling with 3 momentum p. It's 3 momentum because, remember, all of this quantum field theory has been done in a fixed reference frame where I picked a time by defining the Hamiltonian, which then defines the states and so on and so on. Okay, so what else could we ask for? Well, if this is a state with 3 momentum p, yeah, Darren.
But this field is defined over all space.
Yeah.
How can we localize that?
Fantastic. So it's not a localized particle, and we'll see this now. It's going to be a momentum eigenstate, not a position eigenstate. Okay. So again, it's something familiar from quantum mechanics, but it's going to be more like a plane wave momentum state than a localized. Okay, so what would we want from a state that I claim is in an eigenstate of momentum, has 3 momentum p? Well, one thing we'd want is that it's in an eigenstate of the momentum operator. But what's the momentum operator in this case? All I've got is fields. Somebody say? It's not the pi. The pi is the momentum. It's the conjugate momentum to the field phi. So what I want instead is an operator that's going to give me a number. If I've got an object traveling with a momentum 17, I want back the number 17. I don't want something that's a function of space.
We define this operator
like not exactly like in quantum mechanics, but as the integral of p of the ket p, the bra p times p.
Can we do that? No, that wouldn't give the right answer. But we've come across this operator already. Is anybody?
d by dx.
That's kind of quantum mechanical. Okay, I'm after something that's it's a conserved quantity. 3 minutes. Where do we get conserved quantities from? Ah, fantastic, good. So we have this operator. Pi, which was the integral of T0i over all of space. Okay, you remember this? It's the operator, it's the conserved current. Sorry, it's the conserved quantity which arose from invariance under translational symmetries. And that's what we mean by the momentum of a state. Sorry, second?
That is the momentum, not an operator.
Good, so it's the momentum of a classical field, but this is a function of those fields. In fact, for the Klein-Gordon equation, we can write down what the function is. It's the integral over d3x pi of x grad phi. Okay? So it was a conserved quantity that for a given field theory you calculate. This is what it is for the Klein-Gordon theory. And now we turn these into operators. Okay? Now there's a subtlety, but it's the subtlety we've seen already. If you just do this naively, everything's going to give you infinity, but it's the same infinity on every single state. So to have a well-defined momentum operator, we normal order. So we just write down an operator where all the a's are to the right and the a daggers to the left. Yeah?
So is normal ordering a mathematical operation that you might have to do during the calculation? Or is normal ordering a traditional way of writing down Hamiltonians that don't give you infinities?
Good. So for free field theories, it's the way to write down anything that makes sense that doesn't give infinity. You can just take this as the definition of the theory. You can try and play around with other definitions. I don't think anything would work. So it's it's well defined. Colons, all the a's go to the right. It only makes sense in free field theory. And when we come to consider interacting theories, we'll have to figure out what to do. But that'll be the topic of next week.
So you're saying that in interacting field theories, you may have to like do a normal ordering during the calculation?
No, you have to do something else, which we'll come to.
Okay.
Something called Wigston.
So what's being normally ordered here?
The normal ordering means that the a's go to the right and the a daggers go to the left.
Okay.
So there's no a dagger a's. Sorry, there's no a daggers. There's only a dagger a's. Right, if you were to expand this out, this would have some a's and a daggers. This would have some a's and a daggers. Wherever they are, you just move the a daggers.
Okay.
Oh, but so that would be where we like put colons around.
Yeah. So by this I really mean normal ordered objects, but I just wrote it here. So, yeah.
So if you wanted to be precise, you could say that the first, we have 2 lines for after P. And the first one is not the correct momentum operator, and the second
Yeah,
is
and if I really wanted
momentum operator.
to be precise, I could put dots there, and I could put dots here,
No, I mean like,
and then that's true.
forget the dots because they don't mean anything.
Well,
Like,
they do. They mean that all the a's go to the right and all the a daggers go to the left.
well,
So this is now a
I mean, presumably, so you're saying that everything can be written uniquely as a linear combination of a's?
Yeah.
Or is this?
Because all the a's can use amongst themselves and all the a daggers can use amongst themselves. So, yeah.
No, wait a minute. No, even if you write, so you write pi as a linear combination of a's and you write p as a linear combination of a's or delta, but you still, like that, this thingy is still like.
Do the calculation after the lecture, then come and ask me if it doesn't work. But it will work.
I mean, you can certainly do this by hand. I just, why don't, maybe that's a better question. Why don't people simply look at this and notice it gives you the wrong answer and then say, oh, our initial definition of the momentum operator was incorrect. We need to use a different momentum operator, which is given by the second line.
Sometimes that's exactly what I'm doing. But I've just told you in advance what the correct definition is. It's normal order. Okay, so we've got a momentum operator. And we can evaluate this what the momentum of this state is. So you should check this. It's some of you may be able to see it. The state has an A dagger here. You then commute the A dagger past the A. You pick up a factor of 2 pi and a delta function for your troubles, and you'll get this back. Okay. Okay, so this is a state whose energy is the energy of a relativistic particle, and whose momentum is the momentum of a relativistic particle, the 3 momentum here. Okay. What more could you want from the definition of a particle state? Actually, there's one other thing that you can check, which is the angular momentum of this particle. Okay? Now, we've got an angular momentum operator. It came from rotational symmetry of space. And so you could take that angular momentum operator and act on the particle. Now, the angular momentum operator, unlike translation operators, assumes an origin. You know, you rotate around a particular point. So what you'll find if you do this calculation is that there is an angular momentum of the particle, because you're at some point and the particle's going that way. So it's the usual sort of PR type angular momentum. But the really interesting question is, what's the angular momentum if the particle is just standing here stationary in front of you? Because that's something important. That's what we call the spin of the particle. The internal angular momentum, okay, not the orbital angular momentum. So we can compute that. Using the angular momentum operator. So this is the operator that you computed in one of those exercises. Again, you'll have to normal order it. Did you use this notation in the exercise? I can't remember. This is the notation in my lectures, sort of curly M. Anyway, it's whatever the angular momentum operator that you computed in the exercises is. So you'll find that the angular momentum operator acting on the state with 0 momentum. You shouldn't write this state as a 0, because that means something else, right? The 0 is no particles. It's the vacuum state. That's different from when you act on the vacuum state with a dagger, where the p is equal to 0. Okay, one is a state with no particles. The other is a state with a single particle, but just not moving anywhere, just sitting there in front of you. So it's important that it's this. However, you find that it annihilates it. Yeah.
Theory of the classical angular momentum.
That's right, yeah. You have to normal order it.
Right. However, spin, as we know, is something that cannot be described in any classical sense. So, is that convincing?
That's sort of almost true. Right? So, we did it classically, and you get 0. Okay, so that's consistent with what you said. Particles that have spin 1 can be described in a classical sense. They're sort of vector particles that can rotate. And so when we come to describe the photon, we'll see the same calculation gives spin 1. That leaves us with spin 1/2, and that's where you might think there's some problems defining it classically. And we'll see that in some sense, well, I'll get ahead of myself. It's because these operators anti-commute instead of commute, they Grassmann value, there's some difficulty defining it classically. So what you say is sort of right. But what's important here is that spin isn't something we have to sort of pull from the air and put on. It really is just the angular momentum of the particle, where angular momentum is defined as that conserved quantity that you get from rotational invariance.
We don't have to put spin in from outside as an assumption, as we have to do.
Absolutely. Quantum field theory is a superior way. That's to the right state. How am I doing? It would be really good if I could just go on for another 4 minutes or so. Is that good with you guys? Yeah. Okay, what about multi-particles? So how do we create multi-particle states? Well, we just act with a lot of A-daggers. So an n-particle state is labeled by n momenta, and it's given by acting with n creation operators on the vacuum. So every time you act with a creation operator, this is a state with another particle. The subscript on the creation operator tells you the energy of that particle. Sorry, tells you the 3 momentum of that particle. So notice in particular that if I say have a state with 2 particles, the A-daggers all commute amongst each other. That was one of the commutation relations that we got. Which means that it doesn't matter how you order the momentum here. That the state where where the first particle has momentum q and a state where the first particle has momentum p and the second particle has momentum q is exactly the same as the state when you swap them around. But we've got a word for that, right? That's the statement that these particles are bosons. So people have been asking me for a couple of lectures now, what's the Hilbert space on which these operators are acting? So now we can give a pretty good definition of it. So the full Hilbert space of the theory is spanned by, well, it's spanned by the vacuum and the 1-particle states and the 2-particle states, and off you keep going all the way to infinity. Let me get to the end, and then we can answer questions. We're running short of time. And there's a name for Hilbert spaces of this type. They're usually referred to as Fock spaces. Okay, there's one final thing I want to tell you. So suppose I give you a state and you want to know how many particles are in that state. It would be really nice just to have an operator which tells you whether the state has a fixed number of particles or whether it's a superposition of some number of particles. So we're going to just introduce an operator that counts how many particles. So it's called the number operator. And it's the same number operator that you've probably seen in the harmonic oscillator. So it's easy to check that if you act on a state with particle number n with the number operator, it gives you back little n, the number of particles. So notice that this number operator commutes with the Hamiltonian. which means that the particle number is conserved. Now here, I don't mean the particles counting particles with plus and antiparticles with minus. We haven't got any antiparticles in this setup. We've just got particles. This n here is always positive, so I mean that the actual number of particles is conserved in this theory. This is because this is a really dull theory. Nothing's going to happen, okay? So this is true in the free theory, but it won't be true as soon as we go to more complicated theories and turn on interactions. And we'll see that explicitly when we go to the interacting theory. Okay, sorry to run over a bit today. Are there questions before we move on? You had a question.
Oh, right, yeah. So it seems like what you've done, so until now, we had no idea what space our operator was acting, right? And
No, I told you that it was the space of functionals.
Right. But that wasn't, so, well, that's another issue, which I'll ask you about after class. But effectively, we had no idea. You never defined it. Like, we did all these, like, sort of ad hoc calculations. We changed the Hamiltonian to get the right answer. And then finally, we created, it seems like we created the state space completely ad hoc in such a way that it matched. Like,
it's exactly the same thing you do in the harmonic oscillator. And it has to be because what we have here.
Well, in the harmonic oscillator, you have a real, you start with like the space of, square integral functions or whatever.
No, then it's exactly the same as that. We've got a space of square integral functions over, we'll talk about it.
Yeah.
Other questions? No? Coffee? See you tomorrow.